Hello everyone, welcome to Integrated Rate Laws Concentration Time Relationships video. So we've talked about rate expressions, we've talked about the differential rate law, but now we're going to talk about integrated rate law. So the integrated rate law deals with graphing, right? So if you scroll up, this is your kinetics PDF that I sent to you, right? That kind of gives an overview of the entire chapter, of the entire unit. So there's two types of rate laws. There's the differential rate law, and then there's the integrated rate law. So the differential is using table logic or ugly algebra to determine the orders of the reactants and the value of the rate constant K. However, the integrated rate law gives you data, and you have to use graphical methods to determine the order of the reactant. So the differential rate law, you have to use algebra. Integrated rate law, you have to use graphs. So it sounds complicated, but I promise this is almost easier than the differential rate law because you just have to graph it. And if the graph gives you a straight line immediately based on just the data you have a zero order reactant. If you have to take the natural log of that data and then you graph it and it gives you a straight line, you are a first order. But if you take the reciprocal of that data and it gives you a straight line, then you're a second order. So you have to graph each of them. Whichever one gives you a straight line, that's the order that you are. So, and then these are the general equations, the y equals mx plus b, right? So the concentration of A is equal to negative kT plus the initial concentration of A. First order would be the natural log of A is equal to negative kT plus the natural log of the initial concentration of A. And second order is 1 over the concentration of A is equal to kT plus 1 over the initial concentration of A. So keep in mind, or pay attention to, I should say, the slope for zero order is negative k, the slope for first order is negative k, and the slope for second order is positive k. All right. But no matter what you have, negative or positive, take the absolute value to get that slope. So you want absolute value, don't care about the negatives or positives. Alright, this is the example problem that we will be using. So it wants us to determine the rate law and calculate the value of K. It wants us to figure out what is the concentration of N2O5 at 600 seconds. So if we continue to collect data at that point. What is the concentration of N2O5 equal to at a specific concentration? So again, if we continue data points. And then these are our answers right here. So we should get these answers at the end. So we need to form 3 linear regressions in order to do this. We need to learn how to use our graphing calculators. So let's scroll up here using our graphing calculators. We need to set up that time is always in L1. And then L2, L3, and L4 are our y variables. So L1 will be our x-axis, all of our times, so 0 through 400 in this case. Our L2s is just our normal, concentrations. So our L2 will just be this data right here, all of the y concentrations. And then our L3 will be the natural log of those concentrations. L4 will be the reciprocal of those concentrations, and then we're going to graph all of them and see which one gives us a straight line. Alright, let's do some housekeeping. So I'm going to use my online TI-83 emulator. So follow along on your calculator, and let's walk through it. It's also in the packet, so this PDF file that I'm scrolling through, you have this already. So turn your calculators on. I'm going to go ahead and press clear. Clear, right? It says press clear repeatedly until your home screen is cleared. Alright, next go ahead and press second plus 4 to clear all of your lists, and then press enter. And it should say done, right? Pretty easy. Press second 0 and scroll all the way down until you reach diagnostic on. I talked about what that means in a previous video. So it will give you your R values. So go ahead and press diagnostic on and then press enter again. I should say done. Press stat and then edit. so you want to edit your data values, right? You need to put in our concentrations for L1 and for L2. So I'm going to scroll back up here so I can see my data values. So my L1 is my X, which is my time. I'm going to go ahead and enter those data values. So 0, 50, 100, 200, 300, 400, and then I press the arrow over. Oh, whoops, I have to press enter. And then press the arrow over, and then my L2 values are my concentration values of N2O5. So just normal. So 0.1, enter, 0.0707, enter, 0.05, enter, 0.025, enter, 0.0125, enter, and then last but not least 0.00625, enter. Easy peasy. Alright, let's scroll back down. Alright, it says now we have to batch transform the concentrations of the natural log of those concentrations and put them in the L3 column, and then also batch transform the concentration, the reciprocal concentrations, and put it in the L4 column. So let's go over how to do that. So this is our X, this is our Y. Instead of calculating each new value for the natural log of 0.1, the natural log of 0.07, the natural log of 0.05, we can do it all at once together, like a batch, all of them together. So it says to press over and then press up. So your black box should be on the L3 right here. And then you want to press the natural log, second 2, so that means that you're going to take the natural log of all of the L2 values, and parentheses, and then go ahead and press enter. Ta-da! So instead of doing it individually over and over and over, just batch transform it. Alright, let's do the same thing for the reciprocal now. So go put your arrow over to L4, put it up, and then we're going to take second 2, and then the X minus 1 to take the reciprocals, and then press enter, and it batch transform those. Alright, step number 7. It says press stat, and we need to go over to the calc. And then from there, we're going to choose number 4, which is a linear regression, because we don't want an exponential curve, we want a straight line. So whichever one is going to give us a straight line, that is our order of reaction. Alright, so we have regular line, linear equation, y equals mx plus b, or ax plus b in this case. Okay, we are at this step right now. So go ahead, press second 1, so that's our x values, comma, second 2 our y values, comma, and then we're going to press bars over to y bars, enter, enter, and then press enter. Alright, so go ahead and write our r value down, right? That's this right here. So it's a pretty good line, but not quite. I think we can get better. I think the closest we could probably get is 0.9999 continuous. That's going to be the one that we like the most. And we can also graph that, right? So it's an okay line, but let's keep going. Alright, so clear. So we're going to do the same thing. So we're going to press second, enter, to get back up our linear or regular linear equation. But instead of L2, we want L3 this time. Then go ahead and press enter. Ah, this one has a better R value, right? The R value before was, don't remember what it was, but go back up, rewind the video. Our R value wasn't that close to 1. This is really close to 1, right? 0.9999 continuous. I think we have a first order equation. But let's go ahead and check L4. So second, enter to get our thing back up. Go over to L3 and replace it now with L4. Press enter. Yeah, our R values aren't that good. So L3 was the best one. That was the natural logarithmic. And if you have a natural log, that's a first order equation. So when you take the natural log of those concentrations, of those data points, and it gives you almost a perfectly straight line, that means you have a first order reaction. If it gave us an almost perfectly straight line, just normal, that means we had a zero order reaction. If it gave us a perfectly straight line for the reciprocal of those data points, that'd be a second order. So in this case, we have a first order equation. And indeed, if we look at our rate equation, right, rate is equal to the concentration of N2O5 to the first power, right? Our slope is the slope of our ln graph, right? So if we pull this back up, I'm going to go ahead and put L3 back up here. Right, so our slope in this case is our A, so negative 0.00693, and that is indeed our slope, right? So, really accurate. And then we can now that we have our equation, now that we have our rate equation, our rate law, we can go ahead and plug in 600 seconds to solve for the concentration, which you should get as 0.0016 molarity. And we can also plug in a molarity concentration, right, 0.00150 molarity, and solve for what time that would be at. So 606 seconds, right? I hope this helped kind of walk through what's in your PDF. The PDF outlines it really, really well on how exactly to graph it, how exactly to find the linear regression lines, how to find the slope. But I just wanted to walk through it, show you it on my online screen calculator. And if you have any questions at that point, then please come in to class and ask me. All right. See you guys later. Bye.